So let's now start section 4.6 to the end of this chapter. And so we're going to just go ahead and get started. All right, so last section we talked about how cyclohexanes are the most stable ring because it doesn't have any angle strain, as well as it does not because it has the ideal 109 degrees bond angles, and also the torsional strain is not present because of the chair conformation, which allows all of the hydrogens to be staggered from each other. So when we're looking at the chair conformation, which we see drawn here, it has two different types of positions for substituents on the ring. You have the axial positions and the equatorial positions. So if we're looking at the axial and equatorial positions, I want you guys to just really home in and look at this, all right? So if you look at all the protons that are blue in this picture, notice that they're kind of sticking out and going around the ring. And so it's kind of making an equatorial, all right, like the equator of the ring, okay? Whereas the red are sticking up. So they're going to be on the y-axis, all right? So they're going to be going up and down, up and down. And so first this hydrogen goes up, and then the next one goes down, up and down, okay? And so let's look at when we're drawing the chair conformation that we see at the bottom here. And so notice that your axial hydrogens, and I'm circling them right now, these are your red ones here. You're going to have 6 of those. So on every carbon, because 6 carbons, you're going to have an axial hydrogen, which I just circled in purple. You're going to have 6 of those. And then you're going to also have your equatorials, which are going to be 6 because every carbon is going to have 1 axial, 1 equatorial. So you're going to have 6 of both of those. Now, when you're looking at this, notice that the axial hydrogens are going to be perpendicular to the ring. All right. And so as this carbon here is pointing up, you see how the angle is pointing up? This is going up. It is the other one here. That is going to be, see the angle is pointing up here, and then the hydrogen is going up. So all of these are perpendicular, whereas the equatorial ones, which are going to be sticking outward, are kind of close to the plane of the ring. So before we go any further, let's talk about how to draw a cyclohexane. And so there's different ways to draw them, but here's some steps that may help you in the process. So you can start by drawing first 2 slanted parallel lines. From there, notice that the parallel lines stop and they're kind of staggered. They're a little offset from each other, right? This one right here, it starts and it ends kind of staggered. All right. And so after you draw those lines, what you're going to do is the line that's shorter, all right, you're going to create the topmost carbon atom above and the right of the plane of the 4 hydrogens. So you're going to create kind of like this, not really a triangle, but this angle going up and down here. And then you're going to do the same thing here. Now it's important to realize that the one that's on the shorter side of it, all right, this is stopped short of this, is going to have a shorter line from it. And then the one that's a little longer further is going to have a further line. And so again, the one that stops short is going to have a short line. And then from here, you're going to meet where that is. And it creates this chair conformation, okay? All right. So go ahead, you guys can practice that a little bit. All right, so now once you're drawing your chair conformation, so again, slightly slant, excuse me, I'm a bad angle. Trying to draw on my screen. My hand's touching it, won't let me do it. All right, let's try now. Let's try again. It's not letting me draw. There it goes. All right. All right. So once you draw the first parallel line, you're not going to start right at it. It's going to go further. Again, my angle of which I'm drawing is a little off. All right. So your axial bonds are going to go perpendicular to the ring. So you're going to first find your first point here, and you're going to go in the direction of the angle. Second point, go in the direction of the angle. Next one, go up, diagonal direction. So every single time you're drawing your axial lines, it's always in the direction of the angle. So if the angle is pointing down, okay, it's pointing down. You see the arrow pointing down. So the axial is going to go down. If your angle is pointing up, all right, an arrow pointing up, your axial line is going to go up. And so you do that all the way around. Now, equatorial lines are going to kind of go out away from the angle. So if your axial is going up, equatorial is going to go out. If your axial is going down, your equatorial is going to go up. If it's going up, it's going to go out this way, going down, up. And so axial and equatorial. Okay. And I guess in this one, they have it going. All right. But the main thing, this line here, I probably would do it more so like that. Not sure why they drew that on that way. So for this one, I would actually change that to doing this. Okay. All right. So again, axials. Let me change colors. Axials go in the direction of the angle, and equatorials go out and away from the angles. All right. All right, so chair conformations can change. So you can have what we call a ring flip. So a ring flip is when the ring literally is flipping itself. And when it flips itself, the ones that used to be axial, and so I'm gonna, you see how the red in this case are axial? Okay, and the blue are equatorial. Well, notice in the first picture, this angle is pointing up. The green is pointing up, and what I'm calling orange is pointing down. Well, when the ring flips, the ring is being pushed down. So what was green that was up now is pushed down and it's going downward. And the orange that was pushed down is now popping up. And so the ring actually flipped. And so when the ring flipped, the hydrogens are moving with the ring, causing them to get pushed down or pushed up. All right. And so this allows you to have different conformations, just like we had staggered eclipse. You cannot have full rotation, but with the cyclohexane, you can have ring flips. So when we have the bromine in the axial position, all right, so the bromine's in the axial position in the structure here because the bromine is going up with the angle, that is axial. Well, if the ring flips, and if what was axial gets, or if what was pointing up now gets pointed down, and what was pointing down now points up, your bromine goes from the axial position to the equatorial position that you see here. So this angle gets pushed down, and so now it's down like this, and the bromine moves to the other position, the other conformation. Now, when at room temperature, the ring flip is very fast and the structure is seen as a weighted average. Okay, it's a weighted average. Now, if you have different conformations, just like when you have staggered and eclipse, you usually have one that's more stable than the other. All right. And so when they're monosubstituted, these cyclohexanes are not equal in energy. One's going to be more stable than the other. Now, the equatorial conformation is going to be more stable than the axial. Well, why is that case? Well, the secret is in the name. It is 7.6 kilojoules more stable. And that's because if you notice, if I'm looking at this here, you have some torsional strain. This is eclipsed by this. They're both eclipsed. Whereas when they're equatorial, it's actually staggered. It's in between. It's staggered. So let's look at this in another angle. When you have something that has a 1,3 diaxial interaction, that means because the carbon 1 and the carbon 3 are close when the axial hydrogens are every other space, and it results in a steric strain. Excuse me, not torsional, but steric strain. And so because this is axial and this is axial, they're eclipsing each other or they're crowding each other, forming a steric strain. A steric strain. However, when it's equatorial, they are in between and there's no steric strain. They're not crowding each other. So equatorial is always going to be more stable when the large substituent is more stable. Now, if you have disubstituted cyclohexanes, the steric strain affects both substituents, must be taken into account in both conformations. There are two isomers of 1,2-dimethyl cyclohexane, cis and trans. And the cis isomer, both methyl groups are on the same face of the ring, and the compound can exist in two chair conformations. So let's look at that. All right, so here's some some information about different monosubstituted cyclohexanes. Go back, open up the PowerPoint, and you're able to see and be able to measure the type of strain that you're able to do. All right, so back to 1,2-dimethyl cyclohexane. There are both cis and trans, all right? So cis isomer, both methyl groups are on the same face of the ring. Compounds can exist in two chair conformation, axial, equatorial, and equatorial axial. So my methyl groups are on the 1 and the 2. And so the CH3 is going to, the 2 in this case, is going to be axial, and then the other one's equatorial. Well, when there's a ring flip, while this one that was axial now is equatorial, the one that was equatorial is now axial. And so because of that, they're going to have the same strain, because when one flips and changes, the other one changes back. And so it's kind of balanced out, okay, with the total strain. And you can even look here and see where all of those numbers are coming from. You have the Gauss strain, because they're next to each other, so that's 3.8 kilojoules. And then you have two diaxial carbon hydrogen strains here that are happening. That gives you a total interaction of 7.6. And so you have that. Whereas in the other case, because the other one that wasn't axial at first is now axial, you still have that same strain. And so they're completely identical. However, when they're trans, meaning because they're trans from each other, these are both equatorial. So they both do not create any strain with each other, okay? You're not going to have that typical strain with the steric strain. However, when there's a ring flip, they're both axial. And so they're both going to give strain. This is going to be a lot of strain. And so because they're not stable, or they're not equal, they're either no strain or a lot of strain, your conformation in the equatorial position with only the Gauss interactions it's going to be more stable than with the ring flip. And so because of that, it's going to exist mainly in this conformation here. Now, because of the steric strain, as I mentioned, the diaxial conformation is less favorable than the diaequatorial conformation. So the trans 1,2 dimethylcyclohexane will most likely exist in more than 99% in the diaequatorial conformation, making the diaxial conformation almost non-existent. All right. And if we look at this, we see that because of the Gauss interaction, you have 3.8 kilojoules per mole for the diaequatorial. However, with the ring flip, you have a whopping 15.2 kilojoules per mole. And that is definitely a big difference in energy. All right, so when something's 1, 2, and cis, they're going to be either equatorial, axial, axial, equatorial. When it's trans, it's going to be either axial, axial, and equatorial, equatorial. And so in these scenarios, because they're different, the equatorial is going to be more favorable. However, in this case, they're not different, so they're going to be equal. Unless your substitution, if your substituents are not the same, then the one that is larger is going to want to favor the equatorial position. So the larger substituent is going to want to favor the equatorial position. But if the substituents are the same, they're going to be equal. With the 1, 3, your equatorial is going to be favored when it's cis. However, with 1, 3 trans, they're going to be, if they're the same substituent, they're going to be equal. However, if they're different substituents, the largest substituent with the most strain is going to want to be in the equatorial position. And you see that same pattern with the 1, 4 as the 1, 2. Now, because of that, the way to remember it is that when it's cis, you're going to have to look at the largest group, and that's with the 1, 2 and the 1, 4. However, when it's a 1, 3, they're either both going to, with the cis is going to be axial, axial, equatorial, equatorial, and it's going to favor that. So the best way to understand these is to really do some practice problems. And so let's look at a problem. It says, draw the more stable chair conformation of the following molecules. Estimate the amount of strain of each. So I'm going to go ahead and go to the answer. If you guys want to try to pause it and answer it yourselves, you can go ahead and do so. So let's look at A. So to be able to identify which one is better, straight out. To identify which one is better, you're going to have to look at both of the chairs and then flip them. So let's first draw the first chair. So if you notice, it says that it's trans. Therefore, if one's above the ring, the other one's going to below. And so if I click and I go here, one of my graph field groups is up, the other one is below. I also need to make sure they're in the right space from each other. So that's 1, 2, 3. Now, once I do that, I'm going to determine what type of strain I have. So here I have, this is an axial position, so I'm going to have some strain from those. And so because of that, I'm going to have that 7.6 kilojoule strain. However, my chlorine is equatorial, so I don't have to worry about any strain there. So I'm done with that. Now, if I do a ring flip, this is now equatorial and this is axial. And notice that now I'm going to have to calculate the axial energy for my chlorine. Now, with a hydrogen chlorine, because of the size being slightly smaller, the axial strain is going to be different. And so because of that, I'm going to have 2.0 kilojoules per mole. And so a methyl group is more bulky than you have a chlorine group. Hence, because of that, oops. Okay. Because of that, this conformation is going to be more stable. All right. So here are some examples of things that you guys can draw. So I want you guys just to take your time and I want you to go through these and draw them out. So go ahead and pause it and try to draw the more stable conformations. If you're able to do that, then you're on your track, on the right track. If you cannot, please ask for some extra questions, some extra videos to be able to better explain this. All right, and here's some more questions for you guys to go through. So I'll let you guys go through those. And this is kind of asking, is cis or trans 1-isopropyl 3-methylcyclohexane more stable than the other? And then you have some other ones there, and then you have some questions here. So since the bottom ones right there, oops. All right, so these are the questions that I want you guys to answer. And what I think I'll do is I will look at answering these questions and doing an office hour, but I just really want you guys to do them and to work them out and see if you guys can figure them out. So again, these are the first set of questions and these are the second set. So really just practice doing that. By now, you guys should understand how to draw isopropyls, and so that shouldn't be a problem as well. All right, but that is the end of our PowerPoint and the end of chapter 4. However, I definitely know that you guys need some practice problems. So if you have any questions or any comments, please leave it in the chat. I know chapter 4 is a little bit of a whirlwind, and it's going to take you guys really just practicing and working out the problem. So make sure you guys do that and use the student solution manual to check your question answers. All right, I will be starting chapter 5 in the next video. So until chapter 5, see you later.